Hello again. This is Math 2333 coming to you from the College of DuPage. The title of this lecture is 3D Space, and I encourage you to be an active learner as you're watching this video. You recall in most of your math studies to date, you have talked about two-dimensional space. You had an x-axis and a y-axis, and this was flat. And it's flat like the floor of a room. And this was your xy plane. But now what we do is we add a z that's perpendicular to both of those axes, going through what used to be called 0, 0, and now it's going to be called 0, 0, 0, which is the origin, and that's going to be the z-axis. So we have an x-axis that's perpendicular to a y-axis that's perpendicular to a z-axis. Now, you might think that the naming of these is arbitrary, but there are conventions described by the right-hand rule. And so if you take your right hand and curl your fingers around the z-axis such that your fingers roll from the x-axis to the y-axis and your thumb points upward, that is the right-hand rule, and that's the proper orientation for x, y, and z. We describe a point that is called ABC by realizing that this is an ordered triple. So x is A, y is B, and z is C. And so we go out A units on the x-axis, we go positive along the y-axis B units, and we go up C units on this z-axis. Now the physical analogy is if you were in a room and you were facing the corner of the room would be the origin, z would be going up this wall, this would be the left wall, and this would be the right wall, and these walls actually have names as planes. This is called the xz plane, this is called the yz plane, and this is called the xy plane. And these planes are like sheets of paper. And we can find coordinates then. And here we see we're seeking to plot -4, 3, and -5. So that means x is -4. Now we're going into the page -4 units. We're going to go +3 in the y direction, and we're going to go down 5. And so we find ourselves underneath, but this is where you would plot the point -4, 3, and -5. Similarly, if we wanted to plot 3, -2, -6, we would go out 3 on the x-axis. We would go -2 on the y-axis and down 6 on the z-axis, and this is where you would plot 3, -2, -6. Now the point ABC, shown here, determines a rectangular box, and this is the rectangular box that we're talking about. Actually, the rectangular box is this entire box because it's a rectangular box in 3 dimensions. But if we drop a perpendicular from the point P, which is the ABC point, to the xy plane, we get a point Q that has 0 as its z coordinate. And that is AB0. That's called the projection of P onto the xy plane. Similarly, the point R, shown up here as there is R, that's the projection of that point onto the YZ plane, and that is going to be 0, BC, and this point, A0C, are projections onto, and I talked about the YZ plane, and the other one is for the xz plane respectively. Those are projections. This first quadrant here, where everything is positive, is called the first octet. The Cartesian product, R cross R cross R, this is real numbers cross real numbers cross real numbers, is the set of ordered triples x, y, and z, such that x, y, and z are an element of R, is a set of all ordered triples of real numbers, and is denoted as r raised to the exponent 3, or r cubed. So we have given a one-to-one correspondence between the points in space and the ordered triples a, b, c, and r cubed. This is called the three-dimensional rectangular coordinate system. And notice in terms of coordinates, the first octant is the set of all points where all the coordinates are positive. In two-dimensional analytic geometry, the graph of an equation involving x and y is a curve in R2, two-dimensional space. In three-dimensional analytic geometry, an equation involving x, y, and z represents what we call a surface in R cubed. And so now we have a problem for you to ponder. What surfaces in R cubed are represented by the following equation? Z equal 3 and y equal 5. Spend some time trying to do these. I'll be back in a bit. Okay, I'm back. Let's see how you did. So the equation z equal 3 represents a set of x, y, and z where z is equal to 3. Well, that's the set of all points in R3 whose z-coordinate is 3. X and y can be any value. So this is the horizontal plane that is parallel to the x, y plane and 3 units above it. And it is like this. The equation y equal 5 represents a set of all points in R cubed whose y-coordinate is 5. Well, here, all of these are the y-coordinate is 5. This is a vertical plane that is parallel to the xz plane and 5 units to the right of it. And again, if I ask you this question on a test, I would expect you to describe it in this way. Now, when an equation is given, we must understand from the context whether it represents a curve in R2 or a surface in R3. So for example, in the example that we just talked about, y equal 5 represented a plane here, but if we talked about y equal 5 in R2, that would just be a line. And so the context makes all the difference in the world. Here's another example. Which points, x, y, z, satisfy the equation x squared plus y squared equals 1 and z equal 3. It's the and of these two. And part B, what does the equation x squared plus y squared equals 1 represent as a surface in R cubed? Again, you know what to do. Let's see how you did. Because z equal 3, the points that lie in the plane z equal 3, that's where it is, but also x squared plus y squared equals 1, so that is a circle that is up here. So the circle x squared plus y squared equals 1, z equal 3 is given this way, and so we have a circle of radius 1, but this one is centered at 0, 0, 3, and the radius is 1, and it is contained within the plane z equal 3. If we look at the surface x squared plus y squared equals 1 in three-dimensional space, z can be anything at all, positive, and so or negative. Actually, z could be anything, and so it's a cylinder of infinite height. So it's this entire surface. It's the cylinder. Now, it's not everything that's inside, it's just everything that's on the surface of this cylinder. Here's another problem for you to give a go at. Describe and sketch the surface in R cubed represented by y equal 8x. Please give it a go. Let's see how you did. Well, it's going to be a plane going through the origin and intersecting the z-axis at any point on the z-axis. So that's the plane and the answer to the question. We can also talk about distances in three-dimensional spaces, and instead of talking about circles, we'll talk about spheres. Let's begin by talking about the distance formula in 3 dimensions. So the distance, and here we start seeing notation where it's the absolute value of P1, P2, means the distance between the points P, and that's x sub 1, y sub 1, z sub 1, and P2, which is x sub 2, y sub 2, z sub 2, is given by, and it is going to be the square root of, it is x2 minus x1 whole squared plus y2 minus y1 whole squared plus z2 minus z1 whole squared, square root of all of that. And you can see that that actually has to be true because here we're talking about P1 being this point, P2 as being this point. Now you see we can find out, or certainly because of the perpendicular things, we see we have a right triangle that is here, and the red part is the distance between the two. But I can say what is this, and so this is the distance between P1 and this point B, which is going to be the square root of x2, and this is in a plane, so this is going to be x2 minus x1 whole squared. This is y2 minus y1 whole squared, and then the z drops out because it's within that plane. So you see this is going to be that square root. So if I square this and square this distance and add them together and take the square root, use the Pythagorean theorem, I get this formula. This is one that you want to commit to memory. And let's apply that to this circumstance. So we're saying, what is the distance between the point P, 2, minus 1, 7, and the point Q, 1, minus 3, 5? Well, we take the differences. Notice that sometimes you get minus times a minus action going on, and we do this calculation, and we find that the square root of 9 is 3. We can also talk about finding the equation of a sphere of radius r and center h, k, and l. Now h, k, and l can be positive, negative, or zero numbers, but these are that's the center, and by definition a sphere is the set of all points in three-dimensional space whose distance from the center is r. And so what we have is that x minus h whole squared plus y minus k whole squared plus z minus l whole squared is equal to r squared. And so that comes from the distance formula. And again, this is an equation of a sphere. And here is where we state that again. And we do say, in particular, if the center is 0, 0, 0, then it's x squared plus y squared plus z squared is r squared. And here's a problem for you to give a go. Show that x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 is equal to 0 is the equation of a sphere, and find its center and radius. You know what to do. Let's see how you did. Well, this time what you have to do is complete the square on the x's. So we take half of this and square it, and we add it here. Now if we add it here, we have to add 4 to the other side. We complete the square on the y. This is y squared minus 6y, half of this squared, we get 9. So we add the 9 to the other side. And here we have z squared plus 2z. And if we complete the square, we add 1 squared to both sides, and we get this. And we move the minus 6 to the other side to put it in the proper form. We find out that this is a sphere centered at -2, 3, and minus 1. And the radius is going to be the square root of 8, which is also simplified to being 2, the square root of 2. A final example. What region in r cubed is represented by the following inequality? 1 is less than or equal to x squared plus y squared plus z squared less than or equal to 4, and z is less than or equal to 0. You know what to do. Let's see how you did. So the inequalities are saying that this is the outside of a sphere of radius 1, and this is the inside of a sphere of radius 2. And if we took the square roots, we would end up with this. And now we know that z has to be less than or equal to 0, so it's underneath. And we're talking about the points that are inside of the sphere of radius 2 and outside the sphere of radius 1, and the z value is underneath the axis. So the points are the points x, y, and z whose distance from the origin is at least 1 and at most 2. But we know that z is less than or equal to 0, so it lies below the xy plane, and so it represents this figure that is sketched right here. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.